Hello everyone, welcome to another class of fundamentals of particle and fluid solid processing. On today we will be having a couple of examples that I told last time in the last class, that how to use such formula or the definitions that I mentioned in the last class. If you remember, in the last class we had different mean sizes based on some characteristic property like the volume mean diameter, surface mean diameter, length mean diameter, and the other properties like the mean length diameter, mean surface diameter, and mean volume diameter. So we had several expressions for that. Now the point is that how to use or when to use and how to use such expressions. So in today's lecture we will be showing you that how we can implement and how to get such a single value for a collection of particles. So let's start with the first problem. This problem statement says the size analysis of a powdered material on a mass basis is represented by a straight line from 0% mass at 1 micron particle size to 100% mass at 101 micron particle size. So what is the surface mean diameter of the system? So quite logically, when such problem statement is there, what you should do, you should clearly read the problem statement and have a mental visualizations of this whole problem. So what it says, that the size analysis of a sample, of a powdery sample on a mass basis, it says that gives a linear distribution from 0% mass fraction to 100% mass fraction, starting from size 1 micron to 101 micron particle size. So the question is, what is the single number by which we can represent the sample, and that single number you have to determine based on the surface mean diameter of the system. So as I said, you need a visualization of this problem, mental visualization of this problem. So basically it is something like that if you have a sample, you have characterized that the size distribution says that 0% mass from this 1 micron particle to 100% of the mass fraction of this 101 micron particle size. Okay, so particle size 1 micron to 101 micron, we have a linear distribution. So which means this is the size distribution curve that I showed last time. There was some non-linear variation, but in this case it is a linear variation. So we can easily find out what is the expression of this graph or this line. Okay, and this will help us to find out what is the surface mean diameter which is in the question. So again, you have to remember this expression for this, because last time we showed this expression, or I showed you this expression in my last class, that this surface mean diameter, which we can represent, let us say, by dS, is 1 by summation of xi di, where xi is the mass fraction of the ith size component and di is the corresponding diameter. So in this case it starts from 0 of mass fraction where d is 1, and then gradually it increases to 101 micron size particle where xi goes to 1. Okay. Now since it is represented by a continuous function and this expression is by finite difference expression, and this is the size distribution line, we can represent this whole function by this, from these expressions or from these points. This is the linear distribution, so you can easily find out what would be the equation for this straight line for this two points that we have given already, that it is the 0 mass fraction for 1 micron size, and 101 micron size has 100% mass fraction, which is so y axis is the mass fraction from 0 to 1 and x axis is the particle size range in micron. So we have a size distribution, that is d is 100x plus 1. Now how to use this expression here? Now this is a continuous expression, or this is a continuous function. So this expression we can also write in this form, that ds is nothing but 1 by integration of dx by d, okay, from 0 to 1. If we find out this value, we can find out what is the value of ds. Okay. So here we can now see that this expression of d is already obtained here. So we replace this expression of d 100x plus 1 here, and we integrate this function. This integration I will not go into the details, I leave it to you how to do this integration, you know well. So here we get a numerical value which is 100 by this ln of this function, which gives us this 21.7 micron particular value. So that is the answer, that this ds, which is the surface mean diameter for this sample, 21.7 is the mean surface diameter which was in the question. The surface mean, sorry, this is surface mean diameter. Okay. So this is how we calculate in this case the solution. Okay. Now I will move on to another problem. Now here the problem statement says the size distribution of a dust as measured by a microscope is given in the following table. This is the table. So convert this data into distribution on mass basis and calculate specific surface assuming the particles to be spherical with a density of 2650 kg per meter cube. So if you look at this problem and this table, it shows on the left hand side that this is a size range given in micron, and the right hand side the number of particles in the range. Okay. So this distribution is quite straightforward. It is given in a number distribution, that between 0 to 2 micron size particles. So in this range we have counted it is to be around or exactly of 2000 per number of particles. The size of the particles when it goes from 2 to 4 micron, in this range we find that number to be 600. From 4 to 8 micron range, we find the number to be 140 number of particles in that sample. From 8 to 12 micron size particle, in this range we find there are 40 number of particles. So as the size increases, we see lesser and lesser number of particles. From 12 to 16, we find that number to be 15. From 16 to 20, it is 5 number of particles, and 20 to 24 we have 2 particles only. So the size range from 0 to 24 micron particle, we have this summation of all this right hand side number. So this is the total number that we have got from the sample, and this is the size range in which we have determined by the size measurement techniques that we have already also discussed. So the first objective is to convert the data into a distribution on mass basis. Okay. Here it is given in number basis, we have to convert this to mass basis and calculate the subsequent step that we will again come back to this question later. So at first let us focus on this conversion between the number distribution to the mass distribution. Now if you remember the last class, there I showed you the relation between the x, which is the mass fraction, and the n, which is the number distribution. So, the relation between xi and ni here comes into play. Okay. So, let us attack this problem. So, how it is done? The point is that the mass fraction of particles of size di is given by these expressions that we have already seen in the last class, that xi is the mass fraction, ni is the number of I, that particular size of the particle, k is a shape dependent factor, d is the diameter of that sample of particular that size range, and rho is the density of the solid particles. Okay. And here that density is given as 2650. Okay. But we will come to this later, it is not important at this moment, but what you have to understand that this is the relation between the number and the mass fraction ni and the xi. Okay. And now the summation of xi has to be conserved, that is 1. So, the mass fraction we can write in this way, that this is the individual component, okay, and this is the overall sample parameters, okay, which is the summation of ni, k and d multiplied by the rho. So, this is the individual component mass divided by the total component mass. This gives us the mass fraction of that ith component. Okay. So, how it is then solved? So, for that we have to make a table in a tabular form. Now, since this table that we have given, or it is asked in the problem, is in the sizable range, okay, there are only some 1, 2, 3, 4, 5, 6, 7, this 7 range of particles are given. So, that means we can do it by hand calculations, but this procedure, when there is a huge variation in size, that can be done in some software like Excel or some other softwares. So, here we can see that d I have written as 1, 3, 6, 10, 14, 18, 22. How this value came? This came from the arithmetic mean of this size range. If we have to calculate this parameter, we have to find out a d. Okay. Now, for this small range, what could be the d? Okay. As a simple approximation, we can have the arithmetic mean of this size range. From 0 to 2 it is 1, from 2 to 3, 2 to 4 it is the 3, from 4 to 8 it is the 6. So, similarly, we have our first column of this table, which is the d. Okay. Then this n we have written here. This is 2000, this would be 2000, this is a mistake here. So, this is 2000, 600, 140, 40, 15, 5 and 2. Okay. And then we find out what would be this parameter, because eventually we have to calculate this expression to have the mass fraction from the number. So, here we have ni, k, d, rho. Okay. Now, the value of k is not known, okay, because let us say we are solving in a generic way for this problem without knowing or without understanding the second part, that it is written later it is to be spherical to calculate the specific surface. Okay. So, for the time being we neglect this part. For this first part, that means we do not know what is the value of k. So, we will retain k as it is. Okay. And since this is a constant value, it will be eliminated at the end. So, then we calculate this k d cube and rho value multiplied by the n, which gives us such values here. So, dn and rho is given. Even if rho was not known, this could have been a rho parameter and a constant prefactor. Similarly, for all the steps or all the d sizes, we can calculate this particular parameter. Okay. Then we sum it up and we calculate the overall value of k d cube in rho. Fine. So, this gives this parameter, this part, the denominator. So, this denominator is then taken into account while calculating the first value of x. So, this x comes as this parameter, this value divided by this value. It gives the fraction of this first component. So, here what happens that once we calculate this third column, we sum it up, we have the total which is will be at the denominator and this as the numerator, we find this x value, and similarly we find all the fractions for all the components by dividing this value by the summation, this value divided by the summation, this value divided by the summation value, divided by this value gives us 0.229, this value divided by this gives this value, and we will see automatically that this total x will be conserved to be of 1. This is the mass fraction of the total mass fraction of the sample, which has to be 1, the summation of all mass fractions of all the individual particle size components. Okay. So, which means now we have the size range and mass fraction. So, eventually what we have done, we have converted this number distribution to mass fraction distribution. Okay. Then our question was, again if I go back, that calculate specific surface assuming particles to be spherical with a density of this 26, 50, 100, 50 kg per meter cube. So, for that we have to have a mean diameter of this sample, which is the surface mean diameter. Okay. And since in the problem the number distribution was given, we use that information instead of converted mass distribution. So, in the last problem I showed you that the definition of ds with respect to mass fraction xi, but here ds is given in terms of number distribution. So, both these expressions are identical, but it is in converted form. So, from n to x. So, when that happens, so then that means this value we have to calculate again, and here you can now see that d and n is given. So, we can easily calculate this value and this value. Okay. So, this summation of the fourth column and the third column gives us the ratio of these two, gives us the surface mean diameter. So, this overall value of this 180,000 and 056 and 21,968, this ratio gives us the value of ds. So, ds comes out to be 8.2 micron. This is the surface mean diameter. Now, the question was that calculate specific surface assuming particles to be spherical with density 26, 50 kg per meter cube. So, if you now consider that this 8.2 micron, okay, is the diameter of a spherical particle, and then subsequently we calculate its specific surface area, then it becomes that the volume of a sphere of a spherical particle having diameter this is 288.7 micron cubic micron. Okay. And the surface area comes out to be 211 meter per micron square, 0.2 micron square. So, the specific surface is nothing but the surface area per unit volume, which is 0.731 micron square by micron cube. If we convert that per meter square by meter cube, it comes out to be this value. So, from this problem what we have learned, first of all let me again go back to the problem and come again with a step by step. So, the problem was given as the size range and number distribution. The task was to convert this to mass distribution. Then the question was calculate specific surface area assuming that all particles are spherical with a known density. So, for that what we did, at first we converted that number distribution to mass distributions by following this table, okay, by the known relation of n and x. To calculate the specific surface area, we have to have a mean surface, a mean diameter, where now here we have calculated a surface mean diameter, which is based on either the number distribution or the mass distribution. You can calculate by any one of these method. You got a surface mean diameter. From this surface mean diameter, considering that all the particles are spherical in size with that similar dimension or the diameter, you can easily calculate its volume, you can calculate its surface area, then surface area divided by the volume, which is the surface area per unit volume, is the specific surface for this problem that we have calculated. So, if you had not known what is specific surface area, that is also a take home message that we have learned from this problem, that what is specific surface area, that is the surface area per unit volume. And we have learned how to convert number distribution to mass distribution, and I hope you should be able to convert in a reverse manner, that is, if mass distribution is given, you should be able to calculate the number distribution. And in the previous problem we have seen that if a continuous curve is given or a continuous line is given for the size distribution, or any size distribution function is known, how do you calculate any mean diameter? Here we have calculated surface mean diameter. Okay. So, with this I will stop here today, and in the next class again I will be coming up with another couple of examples to make the things more clear to you, and I hope then you will be able to understand the whole conversion as well as the different processes. Thank you for your attention.